Hi, in today's video, I'll be giving a short introduction on eigenvector and eigenvalues, and then how we are doing a step-by-step procedure on how to solve for them. So let's begin by giving an idea of what is an eigenvector. An eigenvector is a vector that is non-zero and satisfies the following equation over here. This equation means that when you multiply V to the matrix A by the matrix A, it results in equaling to a linear combination of V. What does this mean in graphical terms? Let's think about it in 2D. It means you have a vector V, and then when you apply A, this vector stays on the span of V. So it stays on this line, whether it gets changed direction or it increases in length. So this is the definition of an eigenvector, and the eigenvalue is the corresponding value lambda that equals when they satisfy this equation over here. So an example is the one shown below, where our A is a matrix filled with all ones, a V is 1, 1, 1, and you can see that the resulting matrix is 3, 3, 3, which is actually 3 times 1, 1, 1. And so A times V equals to 3 times V. And so V will be considered an eigenvector, and 3 is the eigenvalue corresponding to this eigenvector. But also note that 1, 0, minus 1 and 1, minus 2, 1 are also eigenvectors with the same eigenvalue of 0. And we will see how we can compute this later on. So this is the definition of an eigenvector and an eigenvalue. For more interpretations geometrically on what it does, you can actually visit 3 blue 1 brown video on eigenvector and eigenvalue, as he has a very good demonstration and simulation on what it does. But what I want to do is now show you the step-by-step procedure on how to find it manually. So we start with the equation A V equals to lambda V. This implies when we shift this over to the left hand side, the AV minus lambda, now we want to convert them to the same order. So you times an I, which is the identity, times V. So A and I are in the same order of n. So it's an n times n matrix basically. And this must equal to the 0 vector. So because there are this is now a matrix and this is a matrix, multiplying by the same vector by the distribution, commutative and associative laws, you can just pull them out and group them. So it's A minus lambda I times V equals to the 0 vector. But since V is non-zero and the resulting one is a 0, this square matrix here must be not invertible. And so the determinant of it equals to 0. And so this equation over here is called the characteristic polynomial equation. And then this allows us to solve for lambda, the eigenvalue, and afterwards solve for V, which is the eigenvector. An example is shown. You have the matrix A equals to the matrix filled with all ones times V equals to lambda V. You bring this over to the left hand side, so it's a diagonal matrix with all lambdas. Simplify it, you get this, and then you do the key step of finding the characteristic polynomial equation, which is just taking the determinant of this matrix and letting it be 0. You do the usual steps of finding determinant, where you take this times the cross product of this minus this times the cross product of this plus this times the cross product of this. And after a few simplification, don't worry, I'll be sharing these notes with you so you can read through the steps if you wish. You get this equation, and so lambda equals to 0 or lambda equals to 3. And hence, these are our eigenvalues. Note that these eigenvalues could be complex, but for the beginner like us, we want to keep it simple to keeping it real. If it's complex, you just need to solve the lambda to be a complex value, and you solve the supposed eigenvector for the real parts, if it's possible. So in our case, we just have 0 and 3. Now, let's just take lambda equals to 3 first and sub it back into our A minus lambda I. This is the corresponding matrix. So it times V equals to the 0 vector. And so you need to use the process of Gaussian elimination to get what is V. But you will see that at the end, your V is a solution. It can be infinite number of solutions. And that is right. Because if 111 works, 222 will work, and it will still, and the resulting will just be 666. Because, just a side note over here, AV equals to lambda V, A2V will equal to lambda 2V as well. And so any combination of V times a real number works. And that's what you get at the end. You get a solution space where V equals to T times 111, where T is any real number. So you just need to choose one that is not the 0 vector, and that will just be an eigenvector. And so this solution space is considered the eigenspace generated by the eigenvector and eigenvalue. Similarly, for lambda equals to 0, when you work it out, you get 2 vectors spanning the solution space. And so one of each can be the corresponding eigenvector. And so we can just say that the eigenvectors corresponding to the eigenvalue tree is equals to the span of 111, and for the 10, you just have a span with having 2 vectors spanning it in this space. And that is all for calculating eigenvectors and eigenvalues. It is quite a simple step-by-step procedure, which I'll let you read the notes again to better grasp it. Doing more examples will help you understand it better, the algorithm. And the theory would require sufficient knowledge to fully interpret it, what an eigenvector and eigenvalue is. But let's give an example of a simple application on why we want to even calculate these eigenvectors and eigenvalues in the first place. An example of an application will be if the question or problem requires us to calculate a to the power of 10 times a vector. Now, you don't know what a to the power of 10 is because it will take a very long time. But there is this theorem that we're not going to prove, that if A has n linearly independent vectors, eigenvectors, which like you've seen in our previous case for the 111, there are 3 linearly independent vectors, it means that A is diagonalizable. And what does diagonalizable mean? It means that A can be written as a matrix times a diagonal matrix times the inverse of P. And what more, when you prove this theorem out, you will realize that the diagonal matrix filled with the eigenvalues and the matrix P, which columns are just the eigenvectors, works. And so, this allows us to calculate a to the power of 10 more easily because, as we'll show in the next page, A can be reduced into a matrix times another diagonal matrix to the power of 10 times the inverse of the first matrix P. Let's see. So if A is diagonalizable, A equals to PDP inverse. A squared now equals to PDP inverse times PDP inverse, which actually this P inverse P will cancel out. And so what you'll be reduced is P D squared P inverse. And you see by our induction process, A to the power of n will just be P D to the power n P inverse. But since D is a diagonal matrix, D to the power n will just be the diagonal entry to the power of n. And so this makes computation more easy, and so this is the reason why eigenvectors and eigenvalues are important and are useful in generating large powers of a matrix. So that is all for the short introduction to eigenvectors and eigenvalues. I've hoped you have come to understand how to do it in a step-by-step procedure. And if you like this video, please give us a thumbs up. Do comment on anything that you don't understand. And subscribe. Thank you.